So before I even tell you what Green's theorem says, you probably should know a little bit about George Green. Okay, born in 1793, lived until 1841. He's a British mathematician. What's kind of cool is he actually was self-taught. So he only had 1 year of formal schooling. That's pretty cool.
I had like 12
And then his father was a baker.
What kind of baker?
I don't know. All I have written down is that his father was a baker. Okay? This part is a little bit sad. His work wasn't actually well known at least until after he died.
Well, that seems to be the case a lot.
It does. Yes. So that was your glimpse into George Green's life. Now, let's figure out what Green's theorem actually says. Okay, so let R be a simply connected plane region whose boundary is a simple closed piecewise smooth curve oriented counterclockwise. That is incredibly important. Okay, what does it mean to be simply connected plane region? No holes. Right, so we're talking about something like this. So that's our region R. Again, very important, has to be oriented counterclockwise. When we say oriented counterclockwise, we also say sometimes it's a positive orientation. Sometimes the counterclockwise is hard to see. So another way to think about this is if you have a positive orientation, your region is on the left as you travel around it. And this is going to come into play later in later sections, but just know, positive orientation means as you're traveling around, your region will be on the left. Okay, so then, if P of xy and Q of xy are continuous and have continuous first partials on some open set, bless you, containing R, then the following is true. We have the line integral over the curve C of P of xy dx plus Q of xy dy. We could parameterize C like we've done before. What Green's theorem says is this is the same as the double integral over that region R. Partial of Q with respect to x, subtract partial of P with respect to y, dA. So we can turn the line integral into a double integral over the region R. As you'll see, this is going to be significantly easier most of the time. Okay, because it's been a while since we've done a proof, we should probably prove why this is true. Okay, we have two different scenarios of what our region could look like. Let's say that our region has a definite bound on the left and on the right, maybe where x is equal to a and x is equal to b. And the upper bound is some function of x, the lower bound is some function of x. So our region R might look like that. Or it might have a definite bound in terms of y. In which case our two bounds are functions of y. Ultimately, we need to show the following. First, we need to show that the line integral of f of xy dx, sorry, not f, p, is equal to double integral over the region R of the opposite of the partial of p with respect to y dA. We also need to show that the line integral of q of xy dy is equal to the double integral over the region R of the partial of q with respect to x dA. Now, does that make sense why we need to show those two? These are the two parts that come from here. We're going to match up p and p, q and q. Okay. So we are going to start by proving the first piece. We are going to let C1 and C2 be the boundary curves. So we're going to say it looks something like this. So it's going to look like this region. If it were this one, it would work exactly the same way. Then we have the following. Line integral of p of xy dx is going to be equal to the line integral of over the first curve plus the line integral over the second curve. Do you all agree? I'm going to integrate over the first curve, integrate over the second curve, add them together. That'll give me the whole curve. Okay. It would be more convenient for us if these two curves had the same starting and ending point. So we want them to have the same orientation. So what we're going to do is we're going to manipulate this one a little bit so that we're integrating in the same direction. In this case, we're integrating from left to right. That's what we want to do with the second curve. So this first curve stays the same, or the first integral stays the same. Second one, I want the opposite direction. And we've talked about this. When we do the opposite direction, it changes the value of the integral. Okay. Now we're going to go back to when we first learned line integrals, and we have to parameterize those two curves. So here's going to be our parameterization. For C1, again, C1 looks like this. So our top and bottom functions are functions in terms of x. So we're going to let x be equal to t, and then our y will be g1 of t. Second curve, same thing, x is equal to t, y is equal to g2 of t. And we have t between a and b. And that should go along with the same picture up above. Okay, here's where that takes us then. What we were initially looking for is the line integral of p of xy dx. We're going back to here, and we're going to plug everything in. So we have the integral from t equals a to t equals b. It'll be p of t, comma, g1 of t, dx is just dt, minus the integral from a to b, p of t, comma, g2 of t, again dt, because dx is equal to dt. Okay, I'm going to pull a negative out. So this becomes the integral from a to b of p of t, comma, g2 of t minus p of t, comma, g1 of t. And you'll see why in a minute that this ends up being helpful. Another way to express this is to say that this is p of t, comma, y, evaluating from y equals g1 of t to y equals g2 of t. Do you all agree? Okay. So this then, now we can write as a double integral. So this is a to b. This is g1 of t. This is g2 of t. This is the partial of p with respect to y, and then dy dt. Because when I integrate with respect to y, I'll get p of t comma y, and then I'll plug in. Okay, but initially things were not in terms of t, they were in terms of x. So this is really the integral from a to b. This is g1 of x. This is g2 of x. This is the partial of p with respect to y, dy dx, which ultimately is negative double integral over the region R of the partial of p with respect to y, dA. That was the first statement that we had to prove. Okay. Similarly, if you did the exact same process for the second statement, so if you looked at q of xy dy, you would be able to prove that it's the double integral over the region R, partial of q with respect to x dA. We're not going to go through 10 minutes of that again. Okay. My concern is that not that you can come up with this proof yourself. My concern is that you understand what I did. Do we get the general gist of most of the steps? Okay. More important than the proof is actually being able to use Green's theorem, so that's what we need to do next. We are going to look at the line integral over the region C of y cubed dx, add the quantity x cubed, add 3xy squared dy, where C is as follows. Okay. Before we actually jump into calculating this, one thing I want us to know. This same integral could be written a different way. It could be written as the line integral of f dot dr, where f is y cubed, comma, x cubed plus 3xy squared. So just know, if you see this, has the same meaning as in this case. So when you see that f dot dr, you have the option sometimes of using Green's theorem. Okay, so my first question before we use Green's theorem is, why are we allowed to use Green's theorem? counterclockwise and closed. Closed, simple, counterclockwise, we can use Green's theorem. So this is going to be double integral over the region R, partial of q with respect to x, subtract partial of p with respect to y, dA. Okay. Okay, partial of q with respect to x, that's this one right here. So take the partial with respect to x. When you do, you get 3x squared plus 3y squared. Subtract partial of p with respect to y, which is this one. So that'll be 3y squared dA. So it ends up being double integral of 3x squared. Would you all like to integrate with respect to x first or y? In this case, I don't think it makes a huge difference either way. I would choose y because both functions are y equals. Doesn't make a big difference though. So if we're going this direction, y is going from x cubed to x is going from 0 to 1. So if I integrate with respect to y first, I get 3x squared y going from x cubed to x. When I plug in that x, I get 3x cubed. When I plug in that x cubed, I get 3x to the 5th. And if you trust me, the final answer ends up being 1/4. Okay. A few quick things. What does this calculate? Work. That's our main application. What would our answer change if f were conservative? Yesterday we talked about what does it mean if f is conservative? What's another implication if your vector field is conservative? Right, it's independent of path. Okay, look up here. We start here, we end here. What would the work be? 0. Yeah. So if it's a conservative vector field, you would see right away that it ends up being 0. Do you also remember that to do the conservative field test, you find the partial of q with respect to x, the partial of p with respect to y, and they should end up being 0? So then you can see that the answer is going to be 0 anyway, because when you subtract, you get 0. Does that make sense? Just fun fact for you there. Okay, I want us to talk about some common notation. Did we get the idea of Green's theorem or how to use it? Okay. Common notation. If we have a closed path, sometimes what will be done when you have that vector field, or when you have your line integral rather, is you'll have a notation like that. That means it's a closed vector field. Yeah, circle. Yeah, it's just a little circle. That tells us that it's closed. Sometimes you will also see something like this, and this is when they're really being kind to you. That gives the orientation. So when you see that, that tells you right away closed with counterclockwise orientation. That's an indicator that you should use Green's theorem. Not you should, but you can. Okay, this we already talked about. If f is conservative, Okay. Please know, this is not necessarily 0. This, though, will be 0. So as soon as we know that it's a closed path, same starting and ending point, then we can say the work will be 0. Okay. There's another common application of Green's theorem that I need us to talk about. Okay. Area we've talked about as the double integral over the region R of dA. Another way to calculate area is the line integral of x dy, which is the same as the line integral of negative y dx. And you hopefully want to know why that's the case without just trusting me. This is the case where you set q of xy equal to x and p of xy equal to 0. That's how you end up with that calculation. This would be the other way. Set p of xy equal to y and q of xy equal to 0. This is also 1/2 the line integral of negative y dx plus x dy. Here's how you might see this. Use a line integral to find the area of x squared over a squared, add y squared over b squared equals 1. Okay, hopefully you can tell that this is going to be an ellipse. X-intercepts are a and negative a, y-intercepts are b and negative b. So we certainly could do a double integral, but we are asked to use a line integral. We have any of these options above. I'm going to choose the first one. Doesn't really matter. That's what I'm going to choose. We are going to need to parameterize x and y. X in this case is a cosine t. Y in this case is b sine of t. T is between 0 and 2 pi. So we are going to go from 0 to 2 pi. X is a cosine t. dy is b cosine of t dt. Pull out the ab, so then we just have the integral of 0 to 2 pi cosine squared of t dt. Do you guys remember the trig substitution for cosine squared of t? Okay, it sounds like yes, some of you do. So when we integrate, this ends up being 1/2 t plus 1/4 the sine of 2t being evaluated from 0 to 2 pi, which ends up being pi times a b. Okay, we have two last things to talk about. Any questions so far? Next thing we want to talk about is what happens if we have a multiply connected region. So let's say that you have something like this. Let's say your path is as follows. Maybe you start here. Go around for a little bit. Eventually you're going to have to go to that inner region. Go around that one. You'll have to come back and then finish. With me? Okay. Outside path. That'll be C1 of P of xy dx plus Q of xy dy. And we could use Green's theorem. Okay, here's the important thing to know. This part here, where we have to go in to get to the second path, contributes nothing. It contributes nothing because we take it twice in opposite directions. So you would go in and do that integral, then you would come back and do that integral, but because you switch the path, changes the sign. So that does nothing. We then would have to add that second path. Now I want us to see, though, what that's going to look like when we use Green's theorem. Outside path would be the double integral over the region R. Partial of Q with respect to y, subtract partial of P with respect to x dA. Okay. Ooh. Sorry, I have this backwards, I think. Okay, do we see on the inner path that we couldn't use Green's theorem yet because it's the wrong orientation? So that would end up flipping the sign. So another way to write it would be partial of P with respect to y, subtract partial of Q with respect to x. So rather than flipping the sign, I flipped the sign inside. So that's just the way to look at multiply connected regions. Okay, last thing I want to talk about is what happens if you have a closed curve that has clockwise orientation. You can still use Green's theorem, it's just going to look a little bit different. So here's our last example. We are going to evaluate line integral over the curve C of x to the fourth dx at xy dy, where C is the triangular curve consisting of the line segments from the point 0, 0 to the point 0, 1, then going to 1, 0, and back to 0, 0. Okay, so what I want us to do is draw a picture first so we know what's going on. We go from 0, 0 to 0, 1. then to 1, 0, back to 0, 0. So out of the two main requirements for Green's theorem, we have the closed region, but we do not have positive orientation. So we are oriented clockwise here rather than counterclockwise. In order to get positive orientation, or counterclockwise orientation, we need to use negative c, the opposite path. Then we can use Green's theorem. So this will be the double integral, the opposite region, which gives us a negative sign here. So then we'll have the partial with respect to x, which is y, subtract partial with respect to y, which is 0, dA. So this will be a negative double integral of y dA. That you guys, I think, can probably handle. So we don't need to do it now. Okay, I just wanted to show us the idea, because I do believe there's some in your homework that have a negative orientation that are oriented clockwise. You can still use Green's theorem, just do it the other direction, but know that it'll change the sign. Okay, any questions on Green's theorem?